Good day, ma'am. We are the Group 4, and today we will discuss the membrane separation. So let us first define what is the membrane separation. So membrane separation is a critical technique in petroleum processing. It involves the use of various membranes to separate components based on their size and chemical properties. This process is essential for purifying and refining petroleum products. So, membrane separation is a process used in various industries to separate components of a mixture by utilizing semi-permeable membranes. These membranes allow certain molecules or ions to pass through while blocking others based on their size, shape, charges, or other properties. So now, let us look the membrane separation basic illustration. So in a typical membrane separation, a fluid solution containing a mixture of substances is passed through a membrane under pressure or concentration gradient. The substances that can pass through membrane, known as permeate, are collected on the other side, while the larger molecules or particles are retained as the retentate. This allows for the separation and purification of desired components from the mixture. So, the membrane separation technique finds application in different various forms. So, in water purification, in wastewater treatment, in food and beverage processing, and pharmaceutical manufacturing, and more. So, membrane separation offers several advantages over traditional separation methods such as distillation, filtration, and extraction. So, it is often more energy efficient, environmental friendly, and suitable for separating heat sensitive or volatile substances. So, additionally, membrane processes can be scaled up or down to meet specific production needs.
Good day, everyone. So, other types of membrane separation, we also have the reverse osmosis. Reverse osmosis is a highly effective membrane separation process used for the desalination of seawater and brackish water. It employs a semi-permeable membrane to selectively remove dissolved salts and impurities, producing highly purity water suitable for industrial and drinking applications. So, reverse osmosis also filters have a pore size around of 0.0001 micron. After water passes through After water passes through a reverse osmosis filter, it is essentially pure water. Reverse osmosis also removes most minerals that are present in the water. Reverse osmosis removes monovalent ions, which means that it desalinates the water. Osmosis occurs when a semi-permeable membrane separates two salt solutions of different concentrations. The water will migrate from the weaker solution to the stronger solution until the two solutions are of the same concentration. Because the semi-permeable membrane allows the water to pass through but not the salt. In reverse osmosis, the two solutions are still separated by a semi-permeable membrane, but pressure is applied to reverse the natural flow of the water. This force is the water to move from the more concentrated solution to the weaker. Thus, the contaminants end up on one side of the semi-permeable membrane, and the pure water is on the other side. Nanofiltration is another type of membrane types. Nanofiltration is a membrane separation technique that operates between reverse osmosis and ultrafiltration. It is particularly effective in removing divalent ions, organic matter, and low molecular weight compounds, making it useful for water softening, color removal, and the purification of various industrial streams. A nanofiltration filter has a pore size around 0.001 micron. It removes most organic molecules, nearly all viruses, most of the natural organic matter, and a range of salts. Nanofiltration removes divalent ions, which makes water hard, so nanofiltration is often used to soften hard water. So for the next, we have the ultrafiltration. Ultrafiltration is a membrane separation process that employs a semi-permeable membrane to remove macromolecules, colloids, and suspended solids from liquids. It is commonly used in the treatment of wastewater, the purification of process streams, and the concentration of valuable compounds in the petroleum industry. Ultrafiltration filter has a size around 0.01 micron, while a microfiltration filter has a pore size around 0.1 micron. So, when water undergoes microfiltration, many microorganisms are removed, but viruses remain in the water. But under ultrafiltration, it removes these larger particles and may remove some viruses. Neither microfiltration nor ultrafiltration can remove dissolved substances unless they are first absorbed with activated carbon or coagulated alum or iron salts. So, from the three processes that I have stated, so what does those three remove? So for the ultrafiltration, it removes bacteria, protozoa, and some viruses from the water, while nanofiltration removes these microbes as well as most natural organic matter and some natural minerals, especially divalent ions, which cause hard water. Nanofiltration, however, does not remove dissolved compounds. Reverse osmosis removes turbidity, including microbes in virtually all dissolved substances. However, while reverse osmosis removes many harmful minerals such as salt and lead, it also removes some healthy minerals such as calcium and magnesium. This is why water that is treated by reverse osmosis benefits by going through a magnesium and calcium mineral bed. This adds calcium and magnesium to the water while also increasing the pH and decreasing the corrosive potential of the water. Corrosive water may leach lead and copper from distribution system and household water pipes.
Hello everyone, I will explain how different membrane separation techniques are used in the petroleum industry. We'll talk about three main methods: microfiltration, dialysis, and gas separation. Membrane separation techniques are used to remove unweighted particles, molecules, and gases from various mixtures. These methods help make petroleum product linear, safer, and more efficient. Let's start with microfiltration. Microfiltration is a process that uses membranes with very small pores to filter out largest particle and microorganisms from liquids. These pores usually range from 0.1 to 10 micrometers in size. This technique is particularly important in the petroleum industry. Microfiltration is used for several purposes. First, clarifying process streams. It removes solid and particles to make the liquids clean and clear. This ensures that the final product meets quality and standards. Second, sterilizing liquids. By removing microorganisms, microfiltration helps sterilizing liquids, making them safe for various industrial uses. And the last, removing suspended solids. This prevents solid from causing damage to downstream equipment, which can save on maintenance and repair costs. Next, let's talk about dialysis. Dialysis uses a semi-permeable membrane to selectively remove small molecules and ions based on their size and diffusion rate. This technique is highly effective for purification and recovery processes. Dialysis in the petroleum industry is used for, first, purifying stream water. It removes unweighted small molecules and ions, ensuring that the water is clean and suitable for industrial use. Second, recovering valuable components. By selectively removing certain substances, dialysis can recover valuable components from process streams, making operation more efficient and cost-effective. And the last, removing contaminants. It helps ensure that the final products are free from contaminants and meet strict quality standards. Finally, let's discuss gas separation. This method is used membranes that allow only certain gases to pass through based on their size and solubility. This technique is extremely efficient for separating different gases. Gas separation is vital in the petroleum industry for several reasons. First, purifying natural gas. The membranes remove impurities like carbon dioxide and hydrogen sulfide, ensuring that the natural gas is of high quality and ready for use. Second, recovering hydrogen. Hydrogen is valuable byproduct in many refining processes. Gas separation membranes can efficiently recovering hydrogen for reuse. Last, separating carbon dioxide from flue gases. This application is crucial for reducing greenhouse gas emissions as it allows for the capture and separation of carbon dioxide from industrial emissions. Membrane separation techniques such as microfiltration, dialysis, and gas separations are essential in the petroleum industry. They improve process efficiency, enhance product quality, and help protect the environment. Understanding these technologies is key to optimizing operations and meeting industry standards.
So the other three types of the membrane. So first is the membrane electrodialysis. Membrane electrodialysis is a process used for desalination and purification of water. So as you can see on the picture, it involves the use of an ion exchange membranes and an electrical field to separate ions from water molecules. This technology is commonly used in various applications, including water treatment, wastewater treatment, and other production of high purity water for industrial processes. By selectively allowing specific ions to pass through the membrane while excluding others' membrane, electrodialysis can effectively remove impurities and salt from the water, resulting in cleaner and more purified water. The next one is the membrane pervaporation. Membrane pervaporation is a separation process that utilizes a selective membrane to separate components of a liquid mixture based on their vapor pressure difference. So just like as you can see on the picture, it is commonly used for the dehydration or removal of organic solvent from mixtures. During the membrane pervaporation, a feed mixture is exposed to one side of a membrane while a vacuum is applied on the other side. So the more volatile components in the mixture have higher vapor pressure and easily evaporate through membrane, while the less volatile components remain behind. The vapor that permeates through the membrane is then condensed and collected, resulting in the separation of the components. The advantage of this membrane or the membrane pervaporation lies in its ability to achieve high selectivity and efficiency in separating organic compounds from mixtures. It finds application in various industries, including the chemical processing, pharmaceuticals, food and beverage, and waste treatments. The last type for the membrane is the membrane forward osmosis. Membrane forward osmosis is a separation process that utilizes a semi-permeable membrane to separate water from dissolved solutes or other liquid based on osmotic pressure difference. So unlike the reverse osmosis, which applies pressure to force water through a membrane, forward osmosis relies on the natural osmotic gradient to draw water across a membrane. In this membrane, a concentrated solution or the DOS solution and a diluted solution, which is yung feed solution natin, are separated by a semi-permeable membrane. The osmotic pressure difference between the two solutions causes water molecules from the feed solution to pass through the membrane into the draw solution, thus separating the water from the solutes or other liquids. This process is advantageous because it can operate at lower pressure compared to reverse osmosis, reducing energy requirements. It is often used in applications such as water treatment again, desalination, food processing, and wastewater treatment. And additionally, for more info, forward osmosis have the potential to be more efficient in a certain applications such as concentrating high viscosity liquids or recovering valuable solute from wastewater streams.
In polymer composites, it is a innovative material created by blending polymers with substances like nanoparticles, carbon nanotubes, or fibers. This combination is engineered to enhance the properties of polymeric membranes by addressing limitations in permeability, selectivity, and mechanical strength. Polymer composites offer a range of benefits from enhanced properties because polymer composites possess improved mechanical properties, making it more tough and durable compared to the standard polymeric membranes, and it also exhibit enhanced separation performance, allowing for more efficient filtration. Then it also has customized functionalities because polymer composites has the ability to be customized to suit specific applications by adjusting composition and structure of the composite materials. Engineers can customize its functionalities to meet the unique requirements of different processes. Then there is the versatility because polymer composites find application across various fields including water purification, gas separation, and biomedical devices. Their versatility and customizable nature make them more valuable assets in numerous industrial processes. Then in carbon molecular sieves, or CMS, it is a specialized membrane derived from a carbon-rich materials through a process called pyrolysis. This results in a porous carbon structure with a unique properties ideal for gas separation, particularly for small molecules such as oxygen and nitrogen. Then, CMS has a high selectivity for small gas molecules, allowing them to efficiently separate different components of a gas mixture based on their size and molecular properties. Then it also has good thermal and chemical stability despite its porous nature, making it suitable for use in harsh environments or under high temperatures and corrosive conditions. Then the challenges using CMS is it can be brittle and challenging to scale up for large scale industrial applications. Their fabrication process requires careful and controlled optimization to achieve consistent performance and reliability. Then in cellulite-based membranes, it is constructed from crystalline aluminosilicates with well-defined microporous structures. These membranes are utilized in various applications, including gas separations, evaporation, and catalytic processes. Then it also has high selectivity because cellulite membranes offer exceptional selectivity due to their uniform pore sizes, allowing them to effectively separate molecules based on size, shape, and polarity. And also has the thermal and chemical stability similar to CMS membranes. Cellulite-based membranes exhibit excellent thermal and chemical stability, making them suitable for demanding industrial environments. Then, in fabricating cellulite membranes can be complex and costly because it requires precise control over synthesis conditions and membrane formation processes. However, advancements in fabrication techniques are continually improving the scalability and efficiency of these membranes.
So, for the next topic, which is the dialysis and membrane separation. For the principles of dialysis and membrane separation, it is a process that capitalizes on the selective diffusion of small molecules and ions through a semi-permeable membrane. This process is driven by a concentration gradient, which is difference in concentration of solutes between two solutions, which is the feed solution and the dialysate. The semi-permeable membrane with pores of a specific size allows only certain small molecules and ions to pass through while retaining larger molecules and particles. As the feed solution flows on the side of the membrane and the dialysate on the other, solutes move from the area of higher concentration, which is in the feed, to the area of lower concentration in the dialysate until equilibrium is reached. This gradient-driven movement facilitates the removal of unwanted small solutes and toxins from the feed solution, making dialysis is a critical technique in both medical treatment, for example in the purification of blood for patients with kidney failure, and in various industrial applications where the separation of specific components is required. Next is the application of dialysis and membrane separation. In the petroleum industry, dialysis plays a crucial role in the membrane separation process, primarily for purifying process streams, recovering valuable components, and removing contaminants. This method employs semi-permeable membrane to separate different substances based on their molecular sizes and diffusivity. Specifically, dialysis is used to remove salts, acids, and organic compounds from petroleum mixtures. The process involves placing the petroleum stream on one side of the membrane, allowing unwanted small molecules to diffuse through the membrane into a dialysate solution, thereby separating them from larger into valuable hydrocarbons. This technique enhances the quality of the petroleum products by reducing impurities, increases the efficiency of downstream processing, and ensures compliance with environmental regulations by minimizing the release of harmful substances. And lastly are the advantages of dialysis and membrane separation. Dialysis as a membrane separation process offers several significant advantages in petroleum refining operations. Its gentle nature ensures that sensitive compounds are not degraded, maintaining the integrity and quality of separated products. The process is energy efficient, which helps in reducing operational costs and environmental footprints of refining activities. Dialysis is highly selective, allowing for precise separation of specific molecules based on their size and diffusivity, which is particularly beneficial in refining process where the purification of certain fractions is critical. Additionally, the ability to tailor dialysis membrane to specific applications enhances its versatility, making it suitable for a range of separation tasks within the petroleum industry. This adaptability not only optimizes the efficiency of refining processes, but also allows for the production of high purity outputs, meeting its stringent industry standards and demands.
Reverse osmosis is a process used in membrane separation technology to remove contaminants from water. Here's how it works. Number 1. Membrane. Reverse osmosis involves passing water through a semi-permeable membrane. This membrane has very small pores that allow water molecules to pass through, while blocking larger molecules, ions, and particles. Number 2. Pressure. In reverse osmosis, pressure is applied to the side of the solution with higher solute concentration. This pressure is called the osmotic pressure and is applied to overcome the natural osmotic pressure, which would typically cause water to flow from the side with lower solute concentration to the side with higher solute concentration. Number 3. Separation. As water is forced through the membrane under pressure, contaminants such as salts, minerals, bacteria, and other impurities are left behind, while purified water passes through the membrane. Number 4. Product and reject streams. Reverse osmosis produces two streams: a purified water stream that passes through the membrane and a concentrated stream containing the removed contaminants. And the last is applications. Reverse osmosis is widely used for desalination of seawater and brackish water to produce drinking water and for industrial processes. It is also used for wastewater treatment, removal of contaminants from processed water, and in various other applications where high quality water is required. Reverse osmosis is an effective and efficient method for
water purification, offering high removal rates for a wide range of contaminants. However, it requires energy to protect or to operate the pumps that generate the pressure needed for the process, and it can be sensitive to fouling and scaling of the membrane by certain contaminants. Regular maintenance and monitoring are essential to ensure the continued effectiveness of reverse osmosis system.
So now, we will discuss ultrafiltration in membrane separation process. First, let us recall membrane separation. Membrane separation technology is a membrane-based substance separation process that selectively transports substances through membranes of different properties to achieve the separation and concentration of solutes, solvents, or even solutions. Membrane separation technology can be divided into several types according to the pore size and separation mechanism of the membrane. These types include microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. So now, let us proceed with the ultrafiltration process. Ultrafiltration is a membrane separation process that separates solutes through ultrafiltration membranes. This process is based on a porous ultrafiltration membrane with openings that are between 0.01 and zero point 0.1 microns. For reference, 1 micron or 1 micrometer is equal to 0.001 millimeter. This makes the porous openings in the ultrafiltration process as small as 0.0001 millimeter to 0.001 millimeter. These very tiny openings are effective in removing or separating colloidal substances, high molecular organic matter, and microorganisms in the water. So how does ultrafiltration work? The principle of ultrafiltration technology is to use pressure to drive water through the membrane pores while larger molecular solutes are trapped on the surface of the membrane, thereby achieving the separation of solutes. So this slide includes the simplified process of ultrafiltration. First, the feed stream containing suspended solids, macromolecules, and other impurities is introduced to the ultrafiltration system. Then, the feed stream passes through the semi-permeable ultrafiltration membrane, which selectively allows the permeation of smaller molecules and other ions. Next, the larger molecules and suspended solids are retained by the membrane and form the concentrate stream, which can be further processed or disposed of. Lastly, the purified permeate stream containing the desired components is collected for further processing or use in the petroleum industry. Moreover, ultrafiltration uses hydrostatic pressure to force water through a semi-permeable membrane. The type of membranes that make up the ultrafiltration can be spiral wound, using cross-flow separation, hollow fiber, and tubular membranes. The ultrafiltration system works to remove contaminants with molecular weights from 300 to 500,000 Dalton. The membranes remove very small particles such as chlorine-resistant organisms, bacteria, organics, sediments, high molecular weight solutes, and other suspended solids. Like microfiltration, ultrafiltration is mostly applied as a pretreatment for RO or reverse osmosis, but it can also be a standalone treatment. The ultrafiltration process cannot separate constituents from water as effectively as reverse osmosis. However, the two technologies can be used in tandem, with ultrafiltration removing most of the relatively large constituents of a process stream before the reverse osmosis application selectively removes water from the remaining mixture. The equipment used in the ultrafiltration process mainly includes PVC ultrafiltration membrane components, PVDF ultrafiltration membrane components, and MBR membrane components. So now, we will discuss the applications of ultrafiltration. Ultrafiltration has a wide field of applications. First, ultrafiltration is used in chemical and pharmaceutical manufacturing. One important use of ultrafiltration in the pharmaceutical industry is for the recovery of fermentation broths used in the production of antibiotics. Ultrafiltration is also useful for enzyme synthesis, where it can be used to purify filtrate streams and concentrate retentate streams, separate out proteins or sugar, or dissolve a solution. It is also used in food and beverage processing. In the dairy industry, ultrafiltration is used in a wide range of applications, such as milk protein standardization for cheese production, protein concentration and permeate decalcification, as well as for the lactose reduction in milk. Third, ultrafiltration is used in wastewater treatment. Ultrafiltration is a commonly used technique to remove particles, microorganisms, and macromolecules, making it an ideal choice for drinking and wastewater treatment. Lastly, ultrafiltration is also used in the petroleum industry. While the use of ultrafiltration within the oil and gas industry is somewhat more limited than in other sectors, it does have its place. Among the most common applications are the use of ultrafiltration for potable water generation on offshore rigs or in other areas where there are limited access to water.
So now, let's talk about membrane separation in petroleum processing and the importance of it. So in desalination, membrane separation techniques such as reverse osmosis and nanofiltration are widely used for the desalination of seawater and brackish water, providing a reliable source of high purity water for various petroleum refinery process. Next is the wastewater treatment. So ultrafiltration and microfiltration membranes are employed to remove suspended solids, oils, and other contaminants from petroleum industry. Wastewater, enabling water reclamation and reducing the environmental impact of refining operations. Next is the gas separation. So in gas separation, gas separation technologies, including polymeric, ceramic, and metallic membranes, are instrumental in the purification of natural gas, the recovery of hydrogen, and the separation of carbon dioxide from flue gases in the petroleum industry. And lastly, the catalyst recovery. So, the membrane filtration process are used to recover and recycle expensive catalysts used in various petroleum refining and petrochemical processes, improving process efficiency and reducing waste. And that's the end of our topic and the end of presentation. Thank you.